Welcome to the fifth lesson in our series on electromagnetism. In our previous lesson, we examined Faraday's law, which states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux cutting across a conductor. We saw that we can express Faraday's law mathematically like this: E equals N times delta phi divided by delta T. E stands for the induced EMF, N for the number of turns or windings in a coil, delta phi for the change in magnetic flux divided by delta T, the change in time. Remember, the magnetic flux phi is equal to the product of the magnetic field B and the cross-sectional area A through which the magnetic field passes. As you will probably remember, we conducted a series of experiments, and the results of these experiments confirmed Faraday's law. In these experiments, we observed that the magnitude of the induced EMF can be changed by changing the motion of the magnet, changing the strength of the magnet, and by changing the number of turns or windings in the coil. Now, in today's lesson, we are going to find out about the relationship between the induced EMF and the induced current and apply the right-hand rule to predict the direction of the induced current. By the end of this lesson, you should be able to calculate the magnitude of the induced current using Faraday's law and predict the direction of the induced current using the right-hand rule. Think back to our last lesson. Do you remember how we learned that without an EMF, no current will pass through a conductor? We also said that EMF and potential difference V are both measured in volts. In the case of electromagnetic induction, the induced EMF is actually equal to the induced potential difference across the ends of the conductor. This means that we can use the terms induced EMF and induced potential difference interchangeably. In other words, the two terms refer to the same thing. Now, do you remember that there is a relationship between potential difference and current? This relationship is described by Ohm's law. Can you recall this important law? The current in a conductor I is directly proportional to the potential difference applied across the ends of the conductor V at constant temperature. This law can be expressed mathematically as R, the resistance of a conductor, is equal to the potential difference V divided by the current I. So when moving a magnet in a coil, we can say that the current induced in the coil is directly proportional to the induced potential difference or induced EMF in the coil. We can express Ohm's law for the coil as a mathematical equation as follows: R, the total resistance of the coil, equals E, the induced EMF, divided by I, the induced current. Watch how we can rearrange this to get an expression for I, the induced current. If we want to get I to the other side of the expression, we must multiply it, leaving us with induced current multiplied by resistance, which equals the induced EMF. But to get I, or the induced current, to stand alone, we need to divide by R, or the resistance. The result is I equals E divided by R. Now we can use Ohm's law to calculate the induced current in a coil if we know the total resistance of the coil and have calculated the magnitude of the EMF from Faraday's law. In fact, it is not difficult to combine these two equations. All we need to do is simply divide the Faraday's law equation through by R, the total resistance, to get an equation to calculate the magnitude of the induced current. However, although useful in calculating the magnitude of the induced current, these equations do not give us any idea of the direction of the induced current. For this, we need to examine the work done by Emil Lenz. Lenz was among the early physicists who studied electromagnetic induction. In 1834, he came up with a law which tells us the direction of the induced current. To understand Lenz's work, let's have a look at a simple circuit. Here I have a battery of cells connected in series to a center zero ammeter, a switch, and a coil. When the switch is closed, a current moves from the positive terminal into the ammeter and then through the coil from A to B and then back to the battery. Here, the current moves in an anti-clockwise direction. The ammeter registers a positive reading, so we can say that for this coil, the direction of a positive current is anti-clockwise. We also know that a magnetic field has been produced by the positive current moving in the coil. Here, the magnetic field direction is out of the loop. When the direction of the magnetic field is out of the loop, we say that its direction is positive too. So for this coil, the direction of both the current and the magnetic field is positive. However, when the terminals of the battery are changed around, the current moves in the opposite direction, clockwise, around the coil. Now the needle of the center zero ammeter is deflected to the left, registering a negative current. The magnetic field direction is into the loop, which we call negative. So the direction of the magnetic field and of the current are both negative in this case. Now let's disconnect the battery and the switch and see what happens when a magnetic north pole moves into the coil connected to the center zero ammeter. Now, in other words, we're going to examine the direction of the current induced in a coil. Before the magnet is moved into the coil, the ammeter reads 0 amperes. Now, I'm going to move the north pole of the magnet into the coil. The direction of the magnetic field here is into the coil, and so is negative. Watch what happens to the needle of the ammeter. Hey, the needle moved to the right, indicating that a small positive current has been induced in the coil, and then the needle returned to 0 when the magnet stopped moving. Let's compare what happened here with what happened in the electromagnet. In the electromagnet, when the current was positive, moving in an anti-clockwise direction around the coil, the magnetic field was also positive out of the coil. But when we moved a magnet into the coil, the magnetic field direction was negative, and the current induced in the coil was a positive current, moving in an anti-clockwise direction. Now watch what happens when I pull the magnet out of the coil. The needle moves to the left. Here the ammeter shows a negative reading, which tells us that the current moves clockwise around the coil. Notice that the direction of the magnet's field is still into the loop in a negative direction. Now, why did the ammeter give a positive reading when I inserted the magnet and a negative reading when I withdrew the magnet? Here's a clue. Think about the magnetic effect of a current passing through a coil. You may use the right-hand solenoid rule in your explanation. Here's one explanation. See if you agree with this. When the north pole of the magnet is pushed into the coil, a positive reading is detected on the ammeter. This indicates that the direction of the current around the coil is in an anti-clockwise direction. But remember, whenever a current passes through a coil, a magnetic field is set up around the coil, and the coil becomes an electromagnet. Because we know the direction of the current, we can find the direction of the magnetic field created in the coil. Can you recall in which direction this will be? Remember, for an electromagnet, when the direction of the current is anti-clockwise, positive, the direction of the magnetic field is also positive, pointing out of the coil. This means that this end, where the magnet entered the coil, must be the north pole of the induced magnetic field. So here, the induced magnetic field opposes the magnetic field of the moving magnet. The magnetic field of the moving magnet is repelled by the north pole of the solenoid. In other words, as the north pole of the magnet moves towards the coil, it induces a magnetic field in the coil. This induced magnetic field works to reduce or oppose the inducing action of the magnet by exerting a force on the magnet that is opposite to the direction of the magnet's motion. Now let's apply the same ideas and see if they work to explain what happens when a magnet is withdrawn from the coil. Remember, when I withdrew the magnet from the coil, the ammeter reading changed from a positive to a negative reading. In this case, the direction of the induced current was clockwise around the coil. Using the right-hand solenoid rule, you can see that my thumb points to the end labeled B, where a north pole forms, so this end must be a south pole. The south pole of the solenoid attracts the north pole of the moving magnet, and so tries to stop the magnet leaving the coil. Again, can you see that the induced magnetic field set up in the coil works to reduce or oppose the inducing action of the magnet by exerting a force on the magnet that is opposite in direction to the magnet's motion? These findings are summarized in Lenz's law. Let's have a look at a simple statement of this law. The direction of the induced current will always oppose the inducing action of a moving magnet. Now it is interesting that Lenz's law is actually contained in the full mathematical expression of Faraday's law. Up until now, we have used Faraday's equation to work out the magnitude of the EMF. Let's have another look at the complete equation. Remember, the E stands for the induced EMF. The N stands for the number of turns in a coil, and the delta phi over delta T stands for the rate of change in magnetic flux. I also want you to notice that there is a negative sign in front of the N. This negative sign indicates the direction of the EMF and of the induced current. From this equation, we can say that the induced EMF or current has the opposite sign compared to the rate of change in magnetic flux. Remember, a positive or negative sign are often used to indicate direction. So in this case, we can say the induced EMF or current is in the opposite direction to the change in magnetic flux. What does this mean? Well, when a North Pole magnet enters a coil, the direction of the magnetic field is negative. The magnetic flux increases from a small negative to a large negative value. Change in magnetic flux is the final magnetic flux minus the initial magnetic flux, and in this case will be a large negative value minus a small negative value. So the change in magnetic flux is negative. However, the induced current opposes this negative change and has a positive value, as you can see from the equation and as we have seen when doing the experiment. In the same way, when a magnet leaves a coil, the change in magnetic flux is the difference between a small negative value and a large negative value. So here, the change in magnetic flux is positive. However, the induced current opposes this positive change and so has a negative value as detected by the ammeter and seen in the equation. Now, just in case you are not convinced that the induced current really does oppose the inducing action, I want you to watch this really amazing experiment. You should all know that when any object falls, it accelerates uniformly downwards due to gravity. Here I have an aluminium tube which is not magnetic and a small powerful magnet. Now, when I drop the magnet, it accelerates downwards, just as we would expect for any object when dropped from a height. But watch what happens when I drop the magnet into the tube. Ready, steady, go. What happened to the magnet? At last it falls from the tube. Clearly the moving magnet's inducing action was opposed by the magnetic field set up around the aluminium tube. The opposing force was so strong that the magnet slowed down and did not accelerate downwards at the usual acceleration due to gravity. Now the final thing I want to show you is a quick way to work out the direction of the induced current using the right-hand rule. When a North Pole enters a coil, the direction of the magnetic field is into the coil. In this case, we use the fingers of the right hand to point in the same direction. The induced current will move in the direction that the thumb can curl in. In this case, the thumb points to the right and can bend up. So the induced current moves in an anti-clockwise direction. Of course, you can confirm that this is correct by using the right-hand solenoid rule and checking that the induced pole at the end of the coil does oppose the inducing action of the moving magnet. Now for your task for today. I have connected this coil to a voltage sensor and am going to use the Explorer and a laptop to show how the induced EMF changes when a magnet falls through the coil. Here is the graph of the data that I got from the experiment. Explain why there are two different peaks recorded here. Now that we have a better grasp of electromagnetic induction, we will see how this principle can be used in practical ways in our next lesson. See you then.